Hey everybody, we're back. Part 2 for confidence intervals here. We're going to now find confidence interval that is about the mean. Part 1 was about the proportion, so this is a population mean. Population mean means mu. And we're going to use a t-distribution when sigma is not known, meaning the population standard deviation is unknown. And we have a handy-dandy formula for t. That's going to be the sample mean minus the population mean divided by the sample standard deviation, which is s, divided by root n. That's going to get a little tricky with the calculator, but we'll work its way out. And again, this is called a t-distribution. For a sample size of n. And actually, our t sub alpha over 2 requires a value for the degree of freedom. Which is going to be n minus 1. We'll talk more about that here in a moment. So, I'm going to do a little practice here. And we're going to start here. A sample of size n equals 12. So this right away tells me that my degree of freedom is 11. It's a simple random sample selected from a normally distributed population, which it needs to be for a t-distribution, must be normally distributed. Find the critical value t sub alpha over 2 corresponding to a 95% confidence level. This means that alpha is 0.05, which means alpha over 2 is 0.025. Now what that means is I need to find t sub 0.025 with a degree of freedom of 11 as we're looking at this. So what I'm going to do is go to my t-table, which is my degrees of freedom. And we're here. One tail is 0.025. Two tail makes it 0.05. We're going to go to degree of freedom is 11. That's right here. 2.201. So again, you'll use that table. There is a way to do it in some of the calculators. Some of them have what's called inverse t. As a function, you're welcome to play around with that. You'll need to enter the degrees of freedom in there, but I'm going to use the table. That way everybody has access to it. Next up, it's the same as with a z. N has to be bigger than or equal to 30 if we don't know if it's normally distributed or not to be able to do this. And here's our confidence interval. And this is where E is t sub alpha over 2. Again, we use t when the population standard deviation is not known. This is times standard deviation divided by root n. The degree of freedom, is n minus 1. And we are going to use this formula. Let's see if I can keep that on the screen. Here it is. So a sample of 106 body temperature. So here's my n equals 106. Have a mean. Here's my x bar of 98.2 and a standard deviation. This is my s. Construct a 95%. That means alpha equals 0.05. Which means alpha over 2 is 0.025. And so we're going to construct a 95% confidence interval to estimate the mean body temperature for the entire population. And then we'll get to the second part of the question. So for sure what I'm going to need is t sub alpha over 2 or t sub 0.025 with the degrees of freedom of 105. Now what will happen on our table is we're going to have to get a good guess, and we're going to have to round it to 100 because we don't have the 105. Your calculator can get a much more precise one if we need it. So let's find E. Well, I need T sub 0.025, so that's going to be the same here. Let's see how far I can get that. So I'm in this column here, because that's the 2 tails is 0.05, 1 tail is 0.025. But I need to go all the way down here for the degree of freedom to be 100. That's the best estimate that I can get there. So that's 1.972. 1.972. 1.972. So E is going to be 1.972 times the standard deviation, 0.62, divided by the square root of 106. One 0.972 times 0.62 divided by the square root of 106. So this is our error. And my error here is 0.11875, I'll say. And that'll be the number that I use. So this means that x bar minus E, x bar plus E, is going to be 98.2 plus 0.11875, 98.2, this is minus here, this one's plus 0.11875, which will give me about 98.0, I'll say just 8, and 98.3, these are degrees. Now, here's our confidence interval. So I am 95% confident that the true mean is between, mean population of body temperatures is between 98.08 degrees Fahrenheit and 98.3 degrees Fahrenheit. Now, what does that tell us about the 98.6? I'm pretty sure that that's not the average, the mean body temperature. So 98.6 degrees Fahrenheit, probably not the true mean. There's a few properties about a t-distribution, and a t-distribution is different for different sample sizes, meaning because it depends on the degree of freedom, and the degree of freedom depends on the sample size n. The t-distribution has the same general symmetric bell shape as standard normal function distribution. The t-distribution has a mean of t equals 0, and the standard deviation of the t-distribution varies with the sample size, but is greater than 1. Standard deviation is greater than 0, pardon me. And as the sample size n gets larger, t-distribution gets closer to the standard normal distribution. So as n gets really large, instead of using a t, when n is really large, you could use a z-table, or an inverse norm with it. All right, let's move on to a z. Z means that my sigma is known, meaning my population standard deviation is known. That's the big one here. And we need to have, if we don't know if it's normally distributed or not, n has to be bigger than or equal to 30. And my confidence interval is going to be x bar minus E, x bar plus E, where E is z sub alpha over 2. So now we're back to z because sigma is known. Times sigma over root n, because we're dealing with a sample. So we're going to do practice here. And we're back to the number of chocolate chips and 40 cookies. There's my n is 40. With the mean is my x bar is 23.95. And we're going to construct a 99% confidence interval. This means alpha is 0.01. Alpha over 2 is 0.001, 5, pardon me. And sigma is known in this case to be 2.55. Well, we know that z sub alpha over 2, which is z sub 0.005, we already calculated that out on a previous page, right here. 2.576. So 2.576, let me adjust that. 2.576. And estimating E is going to be 2.576 times sigma, which is known, 2.55, over the square root of 40. 2.576 times 2.55 divided by the square root of 40. 1.386, 1.0386. So this means my confidence interval is, again, x bar minus E, x bar plus E. X bar is 23.95 minus 1.0386. X bar 23.95 plus 1.0386 is going to give me 22.9 and about 25.0 chocolate chips. So the true mean of the number of chocolate chips on these cookies is going to be somewhere between 22.9 and 25 chips per cookie, and I am 99% confident that the true mean is in there somewhere. So I'm going to let you work on these separately. This one separately, you're going to actually put the data in there, and you'll have to get sigma and the mean as you do this. I do want to move on to this last one here, where I find the mean. I find the sample size. It's going to be z sub alpha over 2 times sigma over E. And this is easy to find. This is just using some simple algebra to get this formula. But I want to use this example here. So here's our mean, so of 100. Here's our standard deviation, 15. And we want to find the sample size, so we're looking for n. We want to know the minimum number of people. And we want to be 90% confident. That means that alpha is 0.1, so alpha over 2 is 0.05, which we previously calculated. Right there, 1.645 for z. So z sub 0.05 is about 1.645. And E in this case is 3. So we have sigma, we have E, and now we have z sub alpha over 2. Here's our n. 1.645 times 15 over 3. .645 times 15 divided by 3, close parenthesis, squared. So what's the minimum number of people 67.65, and once again we round up to 68. People. So this is the minimum number of people that we need to give us 90% confidence that our sample mean is within 3 error points, IQ points, from the true mean.